Welcome to week 7 of Precalculus. In this session, our topic is review of sequences in series. For the expected learning outcomes, number 1, illustrate a series. Number 2, differentiate a series from a sequence. Before we proceed with the discussion, let's check first what you already knew about this topic. Check the appropriate column, yes or no, depending on your capability to perform each competency below. Number 1. Can you define a series and a sequence? Number 2. Can you differentiate a series from a sequence? Number 3. Can you give the nth term given an equation? And number 4. Can you give the difference between arithmetic and geometric sequence? So let's begin with this problem. Suppose a newly born pair of rabbits, one male and one female, are put in a field. Rabbits are able to mate at the age of 1 month so that at the end of its second month, a female can produce another pair of rabbits. Suppose that our rabbits never die and that the female always produces one new pair, one male, one female every month from the second month on. How many pairs will there be in 1 year? Solution. They were fully grown after 1 month and did what rabbits do best, so that the next month two more baby rabbits, again a boy and a girl, were born. Eventually, the number of pairs of rabbits in the field are 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. Can you see how the series is formed and how it continues? What pattern do you see? This is an example of Fibonacci sequence. In the Fibonacci sequence, each term is the sum of the two preceding terms. For instance, 1 plus 1 equals 2, 2 plus 3 equals 5, 3 plus 5 equals 8. The first 12 numbers in the Fibonacci sequence are 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and 144. Remember that the question was how many rabbits will there be after 1 year? The answer? In 1 year, there will be 144 pairs of rabbits. What we have actually encountered in the problem are examples of series and sequence. The numbers 1, 1, 2, 3, and so on is again the example of Fibonacci sequence, while the sum, when we added all those numbers, is an example of series. So what is sequence? In everyday language, the term sequence means a succession of things in a definite order. Can be chronological order, size order, or logical order. In mathematical, the term sequence is commonly used to denote a succession of numbers whose order is determined by rule or function. A sequence of numbers is an ordered collection of numbers, t sub 1, t sub 2, up to t sub n, and so on, in which the first number t sub 1 is called the first term, the second number t sub 2 is called the second term, and so forth, and t sub n the nth term. The dots are used to indicate that the sequence continues indefinitely. Based on the number of terms, we have two different types of sequence. First, finite sequence is a sequence with the last term. Example, 4, 9, 16, 25, and 36. Infinite sequence, a sequence which do not have a last term. It has ellipses, indicating that the configuration continues without ends. Example 16, 21, 26, 31, 36, and so on. A series represents the sum of the terms of a sequence. It is separated by plus or minus sign. Minus happens when the numbers are negative. Example 4 plus 9 plus 16 plus 25 plus 36. The sequence with nth term t sub n is usually denoted by the set of t sub n, and the associated series is given by s equals t sub 1 plus t sub 2 plus t sub 3 plus up to t sub n. Let's try the following exercises. Determine the first five terms of each defined sequence and give their associated series. Number 1, the set of n cubed. Number 2, the set of 2n minus 1. Number 3, the set of 1 over 2 raised to n. And number 4, the set of n squared plus 2n minus 3. Number 1, a sub n equals n cubed. We denote the nth term of a sequence by a sub n, and s is equal to a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5, which is the series. First five terms, so a sub 1 is equal to 1 cubed. That is 1 times 1 times 1 equals 1. A sub 2 is equal to 2 cubed. That is 2 times 2 times 2 equals 8. A sub 3 is equal to 3 cubed. That is 3 times 3 times 3, which is 27. A sub 4 is equal to 4 cubed. That is 4 times 4 times 4 equals 64. And a sub 5 is equal to 5 cubed. That is 5 times 5 times 5 equals 125. So again, a sub 1 represents the first term, a sub 2 the second term, a sub 3 the third term, a sub 4 the fourth term, and a sub 5 the fifth term. We have the sequence 1, 8, 27, 64, and 125. The series will be 1 plus 8 plus 27 plus 64 plus 125, giving us a total of 225. Therefore, S equals 225. Number 2. A sub n equals 2n minus 1. The first five terms are a sub 1 equals 2 times 1 minus 1. 2 times 1 is 2 minus 1, that is 1. A sub 2 is equal to 2 times 2 minus 1. 2 times 2 is 4 minus 1 is 3. A sub 3 is 2 times 3 minus 1. 2 times 3 is 6 minus 1 equals 5. A sub 4 is 2 times 4 minus 1. 2 times 4 is 8 minus 1 equals 7. And a sub 5 is 2 times 5 minus 1. 2 times 5 equals 10 minus 1 equals 9. So what we did is substitute 1, 2, 3, 4, and 5 in place of n and then simplify. So the sequence will be 1, 3, 5, 7, and 9. The series, we simply add those numbers 1 plus 3 plus 5 plus 7 plus 9, and the total is S equals 25. Number 3, a sub n equals 1 over 2 raised to n. First five terms, a sub 1 equals 1 over 2 raised to 1 equals 1 half. A sub 2 equals 1 over 2 squared equals 1 over 2 squared is 4. So that's 1/4. A sub 3 is equal to 1 over 2 cubed. 2 times 2 times 2 is 8. So we have 1/8. A sub 4 equals 1 over 2 raised to 4. 2 times 2 times 2 times 2 is equal to 16, giving us 1 over 16. A sub 5 equals 1 over 2 raised to 5. That is 2 times 2 times 2 times 2 times 2. So we have 1 over 32. Our sequence is 1 half, 1 fourth, 1 eighth, 1 16th, 1 over 32. In a series, if we add 1 half plus 1 fourth plus 1 eighth plus 1 16th plus 1 over 32, we have S equals 31 over 32. Take note that the fractions have different denominators, so we have to find first its LCD, which is, in this case, 32, before we proceed with addition. Number 4, a sub n equals n squared plus 2n minus 3. For the first 5 terms, take note that you have to substitute 1, 2, 3, 4, 5 for a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5, respectively, for us to find the answers. A sub 1 equals 1 squared plus 2 times 1 minus 3 equals 0. Because we have 1 times 1 is 1, plus 2 times 1 is 2, so that will be 1 plus 2, 3, minus 3 equals 0. A sub 2 is 2 squared plus 2 times 2 minus 3. 2 squared is 4, plus 2 times 2 is 4, so that's 4 plus 4, 8 minus 3 equals 5. A sub 3, 3 squared plus 2 times 3 minus 3. 3 times 3 is 9, plus 2 times 3 is 6. 9 plus 6 is 15 minus 3, 12. A sub 4 equals 4 squared plus 2 times 4 minus 3, which is 4 squared, 16, plus 2 times 4 is 8. 16 plus 8 is 24 minus 3, that's 21. And a sub 5 is equal to 5 squared plus 2 times 5 minus 3. 5 times 5 is 25, plus 2 times 5 is 10. 25 plus 10 is 35, minus 3 equals 32. The sequence is 0, 5, 12, 21, and 32. For the series, we add 0 plus 5 plus 12 plus 21 plus 32. S is equal to 70. Let's now proceed with one type of sequence. An arithmetic sequence is a sequence in which each term after the first is obtained by adding a constant called the common difference to the preceding term. The following are examples of arithmetic sequence. Number 1, 2, 4, 6, 8, 10, 12, 14. The common difference is 2 because we added 2 on the preceding term. Number 2, 7, 2, negative 3, negative 8, negative 13, and negative 18. The common difference is negative 5 because we less 5 on the preceding term or from the preceding term. Number 3, 6, 10, 14, 18, 22, 26. The common difference is 4 because we added 6 on the preceding term. If the nth term of an arithmetic sequence is a sub n and the common difference is d, then a sub n is equal to a sub 1 plus the quantity of n minus 1 times d, where a sub n is the nth term, a sub 1 is the first term, n is the number of terms, and d is the common difference. The associated arithmetic series with n terms is given by S sub n equals n times the quantity of a sub 1 plus a sub n all over 2. A sub 1 is the first term and a sub n is the nth term or the last term, equals n times the quantity of 2a sub 1 plus the quantity of n minus 1 times d all over 2. Again, n is the number of terms, a sub 1 is the first term, n the number of terms, d is the common difference. These two formulas can be used depending on the situation or the problem. If the given are the first and the last term, you may use the first formula. Again, S sub n equals n times the quantity of a sub 1 plus a sub n all over 2. Let's have an example. Find the 32nd term in the arithmetic sequence 23, 32, 41, and so on. Solution. Let's find first the given. So we have a sub 1 equals 23, n equals 32 because we are looking for the 32nd term. And then d is equal to 9, the common difference, because we added 9 to 23 for us to get 32. Also, add 9 to 32 for us to find 41. So we're looking for the last term or the 32nd term, a sub 32. We have the formula a sub n equals a sub 1 plus the quantity of n minus 1 times d. A sub 32 equals 23, the first term, plus 32, the number of terms, minus 1 times 9, the common difference. A sub 32 equals 23 plus 31 times 9 equals 23 plus 279. Take note, you have to simplify first the one with multiplication. And lastly, a sub 32 equals 302. For the associated arithmetic series, we have s sub 32 equals 32, the number of terms, times 23, the first term, plus 302, the 32nd term or the last term, all over 2 equals 5,200. Let's now proceed with another type of sequence. A geometric sequence is a sequence in which each term after the first is obtained by multiplying the preceding term by a constant called the common ratio. So again, in arithmetic sequence, we add a common difference, and this time we multiply, which is with the use of common ratio. If the nth term of a geometric sequence is a sub n and the common ratio is r, then a sub n equals a sub 1 times r raised to n minus 1, where a sub n is the nth term, equals a sub 1 is the first term, r is the common ratio, n is the number of terms. The associated geometric series with n terms is given by S sub n is equal to n times a sub 1 if r is equal to 1, and S sub n is equal to a sub 1 times the quantity of 1 minus r raised to n all over 1 minus r if r is not equal to 1. That is because if the common ratio is 1, we'll be having a geometric sequence which has the same number from the first term up to the last term. For example, we have 3, 3, 3, 3, 3, 3, 3. So you simply multiply 3 by the number of terms for you to find the geometric series. Let's have an example. Find the 10th term in the geometric sequence negative 15, 45, negative 135, and so on. For the solution, let's identify first the given. A sub 1 is equal to negative 15, that's the first term. N is equal to 10, we are looking for the 10th term, or the number of terms. And then r is equal to negative 3, the common ratio. By the way, how do we find the common ratio? We simply divide the second number by the first number, or the second term by the first term. In general, we divide a term by its preceding term. So that is 45 divided by negative 15, that gives us negative 3. Same with negative 135 divided by 45, that is negative 3. And then we're looking for a sub n or a sub 10, which is in this case our last term. So a sub n is equal to a sub 1 times r raised to n minus 1. A sub 10 is equal to a sub 1, which is negative 15, times r, which is negative 3, raised to 10 minus 1. A sub 10 is equal to negative 15 times the quantity of negative 3 raised to 9. A sub 10 is equal to negative 15 times the quantity of negative 19,683, which is negative 3, the quantity of negative 3 raised to 9. So a sub 10 is equal to the product of 15 and negative 19,683, that is 295,245. Take note, negative times negative is positive. The associated geometric series is, since r is equal to negative 3, which is not equal to 1, the formula we'll use is S sub n equals a sub 1 times the quantity of 1 minus r raised to n all over 1 minus r. S sub 10 is equal to negative 15 times the quantity of 1 minus negative 3, or the quantity of negative 3 raised to 10 all over 1 minus negative 3, equals negative 15 times the quantity of 1 minus 59,049 all over 1 plus 3, equals negative 15 times the quantity of negative 59,048 all over 4, which is equal to 885,720 divided by 4. Final answer, 221,430.